Hi everybody, this is Mr. Nolan, and I want to talk about succession. Now, we're not talking about succession as far as presidential succession, where you have one president succeeds another, and there's sort of a regime change. We're talking about ecological succession. So, this is what we're talking about here, is really ecological succession, and our goal is to be able to analyze and compare the different ways that a biological community changes in response to disturbances. And really just over time. How does an ecosystem change over time? So is this predictable, or is this random, or some mix in between? How do ecosystems change over time? So there's two kinds of scenarios we're going to look at. One is if you have a huge disturbance, which is so enormous that it actually basically gives you a whole blank slate to work with. You have, for instance, a volcanic island appearing in the middle of the Atlantic, and it's just bare rock. And so what happens on that ecosystem, or on that island, in order to have succession, really, in order to have a change in that ecosystem over time. If an island starts as bare rock, well, we know that there's lots of volcanic islands which are not just bare rock. They have things alive on them. They have plants and animals, and they have whole communities. And so there must be some way that this community goes from bare rock, just volcanic rock, to living things. So that's the first kind of succession we're going to look at, is, for instance, if you have a volcanic eruption with bare rock, how does that community appear? We're also going to look at another kind of succession in which you have a disturbance which is not so serious but still pretty big, something like a really disastrous forest fire. So in this forest fire, we're not starting quite from blank slate like with a volcanic island. We already have some things here. It's just that everything has kind of burned down. And we're going to start, from scratch from there. But with the island, this is what we'll start with, is if you have a volcanic island, how does this sort of succession work, and what is this called? Well, first of all, the name for this kind of succession is called primary. It's primary succession. It's the first kind of succession that can happen in order to have any ecological community. So what I have here, actually I want to show you this. I have a worksheet which is linked on the website, which is included in the informational section of this video. And on this worksheet, what you'll find is a whole bunch of data concerning volcanic islands, just like Surtsey, which is pictured here off the coast of Iceland. And this table includes the island name, the country that it belongs to, the year of last eruption, the Shannon Minor Diversity Index, which I discussed in another couple of videos, and the depth of soil, because this is important. And then also what species are there right now, like which species do we find. So if you go and you find that worksheet on my website, you'll find that there's this data and then some blank graphs, right? Some blank graph spaces. There's some questions, and then here's this forest fire examples and some graphs and some questions. But I just want to start up here with talking about volcanic eruptions and what can we learn by looking at these data here. So we will really want to graph this, right? If we can graph it, that's great. But I do want to look at this data table before we go any further. So if we look at, let's just pick any one of these islands. If we take Surtsey off the coast of Iceland, it last erupted in 1967. It's been pretty quiet since then. But basically what we can assume is that the surface of that island is this old. Okay, so the surface of that island is about 40 years or so old, 40, 50 years. And this 50-year change, at one time there were no animals, plants, anything on that island when it was erupting. You can't have plants living on an island that's covered in magma. And also there was a time when it had no soil at all, because when an island erupts, it just covers everything in rock, sort of this basaltic black rock. And so there was a time when there was zero life on that island and no soil. But today we actually see that since 1967 we have some diversity, a relatively low Shannon Minor Diversity Index, but there is some life. And then also we've actually built up some soil. So we have a few centimeters, this isn't meters, this is in centimeters of soil. So there are actually a few centimeters of soil on that island. And there's actually a fair number of organisms. We've got lichens, mosses, we got some insects, we have small grasses, fiddler crabs. But then if we compare that to another island like Zubari, which erupted off the coast of Yemen in 2013, very little Shannon diversity index, and that's because there's really only one species, and that's a species of lichens. And there's almost no soil. It's just a dusting of soil on that island that's been caused by erosion and weathering. Very few species. So that's how to kind of read this table. It's just what species are present, what's the soil depth of the diversity, and then what year did this happen. So let's, in true Nolan style, let's go ahead and graph these. So what I've done here, you can do this by hand, but I did this in Excel. I have actually graphed the diversity and the soil depth since that most recent eruption of that island. Now, we really can't afford to sit around watching how an island's diversity and soil depth change over time, but what we can do is look at all these separate islands and kind of treat each one like a snapshot. That, you know, if an island erupted this long ago, then this is the response of that island to that time. So if we look here at our diversity, if we just look at diversity, it certainly looks to me, so just so that you understand how to read this graph I built, I got a little tricky and I built this graph backwards so that the more distant past is to the right and the more recent year is to the left. So, and then the diversity is on the y. So we want to know how does the year affect the diversity. So we've got our manipulated variable on the bottom and our responding variable on the y-axis. So what we can see here is that if that island erupted really recently, like in the 2000s, it's got like no diversity, very little diversity. It also has very little soil, right, like what we saw. But as we look at islands that erupted more a long time ago, like this dot way back here, this is Krakatoa. So you might have heard of Krakatoa. It was a huge, huge volcano that erupted in 1883. And since that eruption, actually, there's a lot of diversity on that island. It's tropical, and this is basically a tropical island that's got more than 2.5 on the Shannon diversity scale. And so this means that over time, our species have come back after that huge eruption. It might have taken 1 or 200 years, but they actually have come back. So let's go ahead and put an R value on this, and we can see how tightly correlated is this. So I'm going to add my trend lines, display R value. I'm going to blow that up so you can see it. So we have an R value that's close to 1. And what that means, since our R value is so close to 1, is that there's a strong correlation between how long ago that island erupted and its diversity. So if it erupted a long time ago, that diversity has come back. If it erupted recently, it's still not very diverse. The organisms haven't had time to really colonize that island. And if we look over here, I think we see another piece of this puzzle. Why? Why does it take a while for these species to come back? Doesn't it seem they should just be able to just like fly back? So if we go over here, let's look at the soil depth. So in this case, we see a very similar correlation that if the island just erupted, like this cluster of recently erupting islands, they've got like no soil. These ones are sort of intermediate, and this one, Krakatoa, actually has 4 or 5 centimeters of soil on it. And so let's add an R squared value and a trend line. And we see, this is interesting. So our squared value is even higher than the biodiversity. So what this means is there's a very strong correlation between when that island erupted and the thickness of the soil. That as that island sits after its eruption, it sort of, soil appears. And so we have this appearance of soil over time. It's a very strong correlation. So that island, if it just erupted, there's like no soil because it's all rock. But if it erupted a long time ago, we have the appearance of soil. And that's really interesting, that these are both correlated. The more soil, the more diversity, right? Over time, we see more of both. So this kind of begs the question, for me at least, this begs the question of why is that? Why, over the course of time, do we have more soil and more biodiversity? Well, if we look at our data, our species that are present, what do you notice? I want you to pause the video and look at this for a minute. Which species seem to be the first ones that usually show up? Well, I want you to look at that and look at it and think. So the first species that tends to appear, if you look at these islands that just erupted, lichens shows up on that one, nothing shows up on this one, lichens shows up here, lichens and mosses, and most of them have lichens. This is really interesting because it seems to suggest that lichens are really the first organism that shows up on that island. So I bet that Zalzalako and Hungatonga are going to end up with lichens pretty soon. They don't have them at the last time that we checked, but they're probably going to end up with some lichens pretty soon. And then over time, if you look at some islands that erupted earlier, you get mosses and you start getting grasses, mosses. So you get, eventually you get mosses and small plants that show up. And then after those plants show up, you get animals. So this is what is so interesting, is that we have this very strong diversity and soil thickness correlation. We also are able to look at what species are present and say, well, what's there? So let's go ahead and kind of look at this textbook version of what this is. So we're starting with bare rock. And our first species that tend to show up is called our pioneer species, because they pioneer that new space. Those are typically lichens, because lichens secrete organic acids that break down those rocks and actually start to form, cause weathering and erosion to happen. And then plants get a foothold. Little plants are able to show up. And the roots from those plants, mosses and little perennials, are able to actually break up those weakened rocks that have been weakened by the lichens and starts to crunch them up and make soil. That opens up opportunities, more niches for other plants, which over the course of hundreds of years, we get these plants that show up and their roots crunch up the soil, the rocks, and produce soil. So that you still have a bedrock down here, but we're actually producing soil because these plants are able to crunch that up and produce soil. And now this will support animals too, because we have this sort of first level of our trophic level, our ecosystem. We're able to support animals. So that's how primary succession works, right? We can see that through our data. But what about secondary succession? What about a disturbance that's not as bad as a volcanic eruption, but still pretty bad? So something like a forest fire. So this is called secondary succession. So let's jump over to some data and look at secondary succession. So we are looking at forest fires in California. And similar to primary succession, we've got the name, the location, start date, current Shannon-Weiner index, soil depth, and the species that are present. Now notice I don't really see any lichens here, not many at least, but I do see a lot of ferns, a lot of shrubs, grasses, things like that. And as you look at this table, you might be able to tell that how recently a fire happened is kind of a predictor of a Shannon-Weiner diversity index. So if we look at this Orange County San Diego Canyon fire that happens almost at the same time as Krakatoa, a little after, we see that it's got a much higher Shannon-Weiner diversity index than a one that happened 100 years later, the Wheeler fire in Ventura County, 1985, which that only has a Shannon-Weiner diversity index of about 1.5. So that 100-year span of time from 1989 to 1985 has resulted in a whole unit increase in our Shannon-Weiner diversity index. And if we look at soil, I don't know if it's as clear with soil. I don't think that the relationship is very clear. Even the established species present, I don't know if that's all that clear either. But let's go ahead and let's take a look at graphing these. So if I were to take the diversity since the most recent fire, that looks very clear to me. It looks like a very strong correlation. Let's add our trend line. Display our squared value. So I'll blow that up so you can see it. So it looks as though our R squared value is really high. So if a fire happened a long time ago, that means that we've got more diversity. If it just happened a few years ago, let's say in the 2000s, we're not going to have very much diversity. It's going to be a low diversity. So this is a strong correlation. But what about the soil depth? Now, just looking at the soil depth, this looks like ugly data. This is like kind of dirty data. I don't even know how to deal with this. So let's add a trend line and see what this tells us. So our trend line, all right, let's think of how to interpret this. This says that our R squared value equals E times 10 to the negative 5th power, which is a way of saying 0, right? Our R squared value really is 0 for this correlation. So is the time at which the fire happened correlated with the depth of soil in meters? This one actually in meters. And the answer is no. There's no correlation at all. And there shouldn't be, really, when you think about it, because a forest fire should not affect your soil. Shouldn't affect how thick the soil is. But over here, when we looked at the volcanic eruptions, that's definitely an influencer of how thick the soil is, because that lava is going to actually affect the soil, how much soil there is. But here for forest fires, that's not the case. So even though diversity is affected by forest fires, the soil depth is not affected. And so secondary succession, if we look at secondary succession, this works a little differently. We still have pioneer species, little plants, pioneer species, after our fire, our disturbance. However, we have soil already. We don't have to create that soil. So the pioneer species, their job really isn't to create soil. We've already got it. We can build that community relatively quickly because we already have soil. So I hope that this helps you to kind of compare the differences between primary and secondary succession and how we can use data to understand these kinds of succession, how ecosystems change in response to disturbances.